We've looked now at numerical differentiation and its use in statistics, particularly in the context of optimization. So now we'll turn our attention to numerical integration, and arguably that's even more important in statistics than differentiation. So where does it crop up? Well, basically, whenever you need to evaluate an expectation, whenever you need to integrate something out of a distribution or likelihood, any kind of marginalization operation at all, essentially all of these things typically boil down to numerical integration, or at least integration. And if you can't do it analytically, then you want to do it using a computer. So that's fine, but it turns out that numerical integration is typically very, very expensive from a computational point of view, especially in higher dimensions. And so we try all kinds of ways to avoid explicitly doing numerical integration. But in very low dimensions, just 1 or 2 dimensions, for example, just straightforward numerical integration is possible. And in that context, what you typically want to do is to get an accurate as possible estimate of the integral with as few function evaluations as possible. So this will obviously be particularly important if the function that you're integrating is expensive to evaluate. But even if not, it is often the case that these integrals are done as part of some loop, and so you're doing lots and lots of integrals, and so doing it as cheaply as possible with as few function evaluations as possible tends to be a very important requirement. Okay, so we'll start off thinking about very low dimensional integrals. In fact, just start by thinking about 1D integrals, and we'll take it from there. So in 1D, there are 2 sort of obvious lines of attack. So one is to recognize that there's a close relationship between 1D integrals and ordinary differential equations, and so we can in fact simply use ODE solving methods to do our integrals. Right, so if we've got this integral here, just an integral of f of x over the range a to b, we could actually just recognize that that is the solution of this ordinary differential equation here, with the initial condition y a equal to 0, integrated up to b. And there are lots of methods for solving this initial value problem in ODEs. Some are more sophisticated than others, and so all of those can be brought to bear on this problem, and so that can be a very productive route. It's a bit of a 1D specific approach, but it can be very effective. Now, that's fine, and these methods are typically very, very accurate, but they're not always super efficient in terms of the number of function evaluations required. And so the alternative approach is to use some kind of quadrature method. So what do we mean by a quadrature method? Well, we just mean we have a set of points that we're interested in. We evaluate the function at that set of points, and we use those. We combine them in some way, usually weighting them together in a linear way, in order to get some estimate of the integral. So this is very much the idea of thinking of the integral as an area under a curve. We estimate the area under the curve on the basis of a small number of function evaluations. So yeah, one of the simplest ways we could do that is using the so-called midpoint rule. So the midpoint rule says, well, I could even draw a little picture. We have our range a to b that we're interested in. We have the function f of x, and we simply divide up our integration range into some rectangles. And what we're going to do is we're going to, in this particular case, use function evaluations at the midpoint of those intervals to choose the height of the rectangles. And there are other things you could do, and there are maybe other things that you are familiar with, but that's the midpoint rule. And actually, if you think about it, you can see it's really very closely related to the trapezium rule, which I know is another popular method. It's not quite as good as Simpson's rule. That's a higher order variant. But the midpoint rule is a pretty standard quadrature method that works reasonably well on many reasonably smooth functions. Okay, so that's all we're saying there. We're going to take a bunch of function evaluations. We're going to treat those as the heights of rectangles that we can use in order to get some estimate of the area under the curve that we're interested in. And it's not going to be perfect because these rectangles don't precisely describe the curve that we're trying to integrate, but it's usually going to give us a reasonable approximation as n increases. Right, so that's a simple example of a quadrature rule, but there are variants that are more sophisticated. Okay, so in 1D that's fine. Once you go up to higher dimensions, then these naive approaches sort of break down very quickly. So we'll look a little bit at this, but once you get into high dimensions, then really you end up using some kind of analytical approximation or a Monte Carlo method. And we'll look at both of these. So you can just take your function that you want to integrate, and if you can't analytically integrate it, then you approximate it by something that you can analytically integrate, and then you analytically integrate it, right? So that's the idea behind a Laplace approximation. So we'll look at that. The other thing you could do is switch to Monte Carlo, and again that's going to be a little bit tangential to the main thrust of this course, but it's really for high dimensional spaces it's the only practical solution, and so what you do is you somehow construct some random statistical estimate of the integral. And if you can do that, for example, in an unbiased way, then that might be a useful property. But the crucial advantage of this Monte Carlo approach is that it scales much better with dimension than a simple quadrature approach, and so that's going to turn out for high dimensional problems to win out over other kind of approaches. Yeah, so we'll look at that as well. Right, but let's start off thinking about quadrature. So here's our midpoint rule again. We can just see how this works in R. Interestingly, although we're not going to get into the error analysis, this midpoint approach has order h squared error, where h is the width of your rectangles, right? So in this case, b minus a over 2. So it has order h squared error. Which means because it's b minus a over n, okay, that means it has order n to the minus 2 error. So that's going to be important later. So just remember that the error is going to be order n to the minus 2. So let's pick a very, very simple integral, just integrating e to the x, which we could obviously do analytically, but let's pretend that we don't know how to. We know what the real answer is here, so we can see how our midpoint rule does. So if we just start off with 10 as our number of intervals, we can just turn that expression here into R code. We can see what we get, and we can compare it with the truth. Okay, so what we see here is that we get this is our estimate, this is the truth, and so this is our relative error. Okay, and the relative error, you see, there are 3 zeros there, so we're not doing too badly, but it's not super accurate. So what happens then if we ramp up the number of intervals? So if we ramp up now to having 100 intervals, we just have the same again, and now our error is order 10 to the minus 6. That's great. We ramp up again to 10 to the 3 intervals, and our error is order 10 to the minus 8. Yeah, so you see that the error is going down 100-fold for every 10-fold increase in the number of function evaluations. Okay. And yeah, just to mention in passing, this is a deterministic procedure. So this error, we probably shouldn't think of as sort of statistical error. We should really think of it as a bias in this procedure. Right, so that is the midpoint method. And like I said, it works reasonably well for, sensible, smoothish functions. Right, so we could stop there. We could also use Simpson's rule, which is slightly higher order. That uses kind of local polynomial fits to get a slightly better estimate of the area under the curve. But in fact, it turns out there's a whole other class of methods that are motivated somewhat differently that can perform astonishingly well in certain situations. They can also fail badly, so they're not magic, but you'll see they appear to be magic if you try them on smooth functions. So Gauss quadrature, or sometimes called Gaussian quadrature, is a different strategy for numerical integration. So rather than dividing up your area under the curve into rectangles that you then add up or whatever, the approach is somewhat different. It says, well, given a set of evaluation points or nodes and a set of weights, can we figure out a set of nodes and weights such that the weighted combination of function evaluations at those nodes weighted by those weights will exactly evaluate an integral that I'm interested in for a certain class of functions. All right, so obviously this is strict equality here. You're not going to be able to do this in general for anything. You just use a finite number of function evaluations to evaluate any integral that you're interested in. Clearly that's not going to work. But you can ask the question that for a given class of functions and a given weight function, can we find a set of nodes and weights that will give me exact equality here for all functions G within this class? And the obvious class of functions to start thinking about are polynomials. So you could say, okay, can I, for polynomials up to order 2n minus 1, do this on the basis of n function evaluations? And the answer is you can, which is probably a bit surprising, but it turns out that you can. So just to make sure we know what that means, suppose n was 1. So can we, on the basis of one single function evaluation, figure out exactly what the integral of any particular class of functions are? And here, if n is 1, then we're saying up to order 2n minus 1, so that would be, well, here just linear. So what we're saying is that with a single function evaluation, we can evaluate any linear integral perfectly. And so again, is that surprising? Well, it's not really if you draw a picture. So again, we're thinking of any linear function integrated over that region. How could we possibly do that with just a single function evaluation? Well, actually, if we choose it to be the midpoint, right? So choice of the nodes is very important. If we knew the midpoint, and then actually we could just take the area of that rectangle. So you just weight the function evaluation at the midpoint by the width of the interval, and that would actually give us the exact integral, right? Because although we've drawn it as a rectangle there, those two triangles have the same area. So this is going to be exact, and it wouldn't matter if it was this linear function or this linear function, right? The area is always going to be the same. So if we know the value of your linear function at the midpoint of your integral, you can work out exactly what its integral is. So that's a very special case. So if we move up one, we say, well, with 2 function evaluations, we ought to be able to do this up to 4 minus 1, which is 3. So it turns out with just 2 function evaluations, you can figure out the integral of any cubic, right? Any polynomial up to cubic, which again seems pretty surprising, but it turns out that is possible as well. Okay, so that's the idea. So with just n function evaluations, you can figure out the integral of any polynomial up to order 2n minus 1 exactly. But then, of course, you can say, well, how do we get the weights? How do we get the nodes? Well, yeah, that's a bit beyond the scope of this course, but we'll see how we can do this computationally in R. But the other question is, well, actually, what if the thing I want to integrate isn't a polynomial, right? And that is typically the case. Well, in that case, the question you need to ask yourself is, can it be well approximated by a polynomial of this order? And if it can, then quadrature will probably still work well, but you won't have an equality here. It'll now be approximate. So any function that can be reasonably well approximated by a polynomial, as long as you have enough function evaluations that it be well approximated by a polynomial of this order, then actually that should all work fine. So that's the idea. So how do we do this in R? Well, in fact, it turns out there's an R package called StatMod that contains a function called Gauss Quad that will give us these weights and nodes. So where these weights and nodes come from is not the topic of this course, but it all comes from like polynomial theory. But once we've got the weights and the nodes, then we can use them to actually carry out integrals using a very small number of function evaluations. And here, we're going to be typically assuming that our weight constant is our weight function is a constant. So we just want an integral of g. Okay, so we just want to integrate g over the interval a b, and that's what we're going to use Gauss quadrature for. So if we load up this package StatMod, we get this function Gauss.quad, and so we can say, okay, let's have n points, and then what we need are the nodes. So these are the places where we're going to evaluate our function, and the weights. Okay, and so by default, what this package gives you are the nodes and weights for integrating over the interval -1 to 1. Right, so if you want to integrate over -1 to 1, then you're good to go. And these weights, in fact, if you sum them, you see they sum up to 2, because that is the total weight you want for an interval of width 2. If you don't want to integrate over the range -1 to 1, it's not such a big deal just to rescale these weights. Okay, and we'll see how to do that. So let's take our example of this exponential function that we wanted to integrate. How to integrate it? Well, we just take a weighted set of function evaluations, but we've got to mess about rescaling these nodes. So we add 1 to the nodes to shift them along, but then we're still too wide, so we divide them by 2. So now they're over the range 0 to 1, which is where we wanted to integrate. So we can now sum that up, but in fact, because the total combined weight of that is 2 and we only wanted a total weight of 1, we also need to divide the answer by 2. So that's a little bit fiddly. We'll see how to automate that in a second. But again, it gives us the answer, which looks pretty good. It's actually order 10 to the -15. So even though we only had 10 function evaluations here, we've got a phenomenally accurate estimate of the integral. And that's because the exponential function is very well approximated by a polynomial of order, well, I guess it'd be 19 or something, right? Which is not totally surprising. But so because of that, we get an extremely accurate estimate of the integral. So it's a bit of a faff to rescale this every time you want to do it. So we can easily just write a little function to do this rescaling logic. So if we want to integrate over some arbitrary interval from a to b, and we may as well, default to -1 and 1, we can just get our weights and nodes, rescale the weights, rescale the nodes, and then evaluate our integral. Okay, so here, this is how we'd use this little function. We want to integrate this exponential function. We want to use Gauss quadrature with 10 function evaluations, and the actual interval we're interested in is the range 0, 1. Okay, and so if we call it like that, we get our estimate. Right, so that deals with the rescaling issue. So 10 function evaluations was clearly too many, right? We got this phenomenally accurate integral estimate on the basis of 10 function evaluations. So is 5 enough? Well, yeah, with 5, we still got an error of 10 to the -13. So even 5 function evaluations seems like too many. So how about just 3 function evaluations? And even with 3 function evaluations, our error is order 10 to the -7, right? So with 3 function evaluations, this quadrature estimate is more accurate than the midpoint rule with 100 evaluations. And so the exponential function, it's very cheap, so this maybe doesn't seem like such a big deal, but for an expensive function, or if this is actually the inner loop of some very computationally intensive code, this is a massive difference, right? 3 evaluations versus 100, and the 3 is still more accurate, right? So Gauss quadrature does seem like magic when you see it on these nice smooth examples. However, it doesn't always work so impressively if your function isn't so smooth, and in some cases it fails. It breaks down quicker than the midpoint rule, and we'll see an example of that later. So when it works well, but it can fail badly, and in some ways the midpoint rule can be a bit of a safer bet when you're not really sure how well quadrature is working. How do we adapt this to multi-dimensional integrals then? I mean, the conclusion is going to be that for more than 2 or 3 dimensions, quadrature is not such a great strategy anyway. But let's at least think about how we could do quadrature in a small number of dimensions. And in fact, in 2 and 3 dimensions, you can get it to work reasonably well. Well, the idea is you just break down your multi-dimensional integral into a sequence of one-dimensional integrals, right? It's the obvious thing. And you can use your weights from your Gauss quadrature to do this, or indeed the weights from your midpoint rule to do this, right? You've got equal weights if you're using a midpoint rule. So this basic approach just works. You just break down your double integral, say, into a double sum. And so you just got the product of weights here that you're weighting by your function evaluations. Okay. And in principle, we could do this for as many dimensions as we like, but clearly the problem here, and it's the fundamental problem with these quadrature approaches, is that you really need to maintain the number of evaluations in each dimension, n, and so that means your total number of function evaluations is going to go up like n to the d. So this is the so-called curse of dimensionality, and all of these quadrature style approaches really suffer from this curse of dimensionality as the dimension d increases. So even if we were in a situation where 3-point Gauss quadrature worked fantastically well, by the time you're up to, say, a 13-dimensional integral, you're still into the millions of function evaluations, right? So this is scaling really badly as the dimension goes up. But if we want to pursue it, again, we can write little functions to help us do this approach. So we could create a little mesh function here, which creates the kind of matrix of nodes of basically the set of coordinates, the set of points at which we want to evaluate our multidimensional function, and the corresponding set of weights. And well, let's just see how it works. So for example, if we did a mesh on the nodes 1, 2, and we wanted the 3-dimensional version, then we'd get this set of nodes here, right? So what this means is that in each of 3 dimensions, we're interested in the points 1 and 2, and so we've got 1 and 2 in each dimension, and we just run through all of the combinations of those, and because we've just gone with an equal weight function here, we just get an equal set of weights on each of those 8 possibilities, yeah, because there are 2 to the 3 possibilities, of course. Okay, so it does the obvious thing, but we can use that for the nodes and weights for the midpoint rule, which is very simple. We can also use it for the nodes and weights for a quadrature rule as well. So let's start off with the midpoint rule. So we need a multi-dimensional function to integrate. So for this one, let's just integrate over -1, 1 to the d, just to save us having to worry about the rescaling issue. And we'll integrate this function here, which is just the exp of the sum of x's, right? So that's just a nice simple multi-dimensional function. We can define it in one line of our code like so. So let's try the midpoint rule first of all, just in 2D. So in 2D, suppose we want 10 function evaluations in each dimension, then that's going to give us 100 evaluations overall. Again, we know what the true answer is here. We create our mesh. Okay, so this is our set of mesh points equally spaced. This is our dimension, and our weights are going to be equal. And so we now take our mesh weights and nodes and weight them and sum them to get our integral estimate. And again, because we know the truth here, we can compare our estimate to the truth, and we get a reasonable answer. Not fantastically accurate, but it's not a terrible answer that we get back. Okay. But as the dimension goes up, our function evaluations go up. So to maintain a similar error, we need to maintain 10 evaluations for each dimension. And so now, for a 5-dimensional integral, we're up to 10 to the 5 function evaluations. Yeah, and so that maintains the error. So that's what you need to do. You need to think about what would be the sensible number of mesh points for a 1D integral, but then your actual total number of function evaluations for your d-dimensional integral is going to be at least order n to the d. So it's going to go up exponentially with dimension, and that is the problem. So again, if we can just use the same procedure, it works fine, and as long as our number of function evaluations goes up exponentially, our error will stay tolerably low. So Gauss quadrature is potentially better because we can get away with a smaller number of function evaluations for each dimension that we have. And so here, if we just start off with 4 evaluations for each dimension, then for the 2D, that's obviously just 16, and that gives us a very good error. Okay, so that's good. We go up to a 5-dimensional integral. So this is now just 1024 evaluations to keep the error, but it has exactly the same property that we need to maintain this number of evaluations for each dimension in order to maintain our error as the dimension goes up. So even with Gauss quadrature, it's kind of putting off the problem a little bit longer, but still, by the time we're up to 20 dimensions, we're still requiring an insane number of evaluations in order to keep our error tolerably low. Obviously, we could get away with fewer evaluations, but our error is going to go up if we do that. So quadrature really doesn't work as the dimension goes up. So, what do you do in that case? Well, as we'll see, ultimately you will wind up resorting to Monte Carlo methods, but let's put that off for the time being, and let's think about some kind of analytical approximation. So Laplace approximation is the go-to method when you have statistical problems where you want to integrate out random variables. Essentially, you want to marginalize over something. Laplace approximation is a good general purpose strategy that often works pretty well. So yeah, the typical setup is that you have some joint probability density or likelihood function for something that you're interested in some way, and some nuisance parameters of some description, here B, that you are not interested in, and so you want to integrate out. So here, this might be, for example, some random effects that you don't care about. So you're really only interested in the observed data here, Y. And so to get at that observed data density or likelihood, you've got to integrate out B. In the usual statistical context, there'd be some sort of parameters theta that are implicit here, that they're not explicitly given. And so the idea is that you'd want to vary theta and look at how the observed data likelihood changed as you change theta. But the observed data likelihood requires integrating out B. So we're just suppressing the theta here. It's not important for this discussion, but typically there'd be sort of some parameters theta underpinning this as well. But anyway, the basic problem is we've got some joint density, and we want to integrate out some of the variables. We want to do some kind of marginalization operation. Whenever we're in this situation, the Laplace approximation is the standard way of doing this. So what can you do? Well, for fixed given y, so that is, again, we're thinking about this being a likelihood where you observe y. For fixed given y, what we can do is maximize this function, which is now just a function of b, to find the mode by, and we can do that, for example, using Newton's method. And then once we have that mode for that function, we can expand the function about that mode to get its behavior as a function of b. And essentially what we're going to do is a second order Taylor series expansion, because we know at the mode there's no gradient term, right? So we've just got our value of the density at the mode plus this second order correction term involving the Hessian. And so that's Taylor's theorem. There are sign problems here, of course, because in optimization we think about minimizing, but when we're doing likelihoods we're maximizing. So you'll see the sign of h flipping back and forth as we do things with this problem, but you can track it through carefully yourself. But so this is our Taylor series approximation to the log density, and we do the Taylor theorem on the log density because, well, for all kinds of reasons, but essentially it's just likely to be much more quadratic. Yeah, density is strictly non-negative. The log density is much likely to be better. If you know anything about normal theory, you know that the log of the normal density actually is a quadratic form. So there are all kinds of reasons why the log of the density is the natural thing to look at and the natural place to apply Taylor's theorem. So that's our approximation, but back on the original scale, we could write it like this. So it's the exponential of this quadratic form, which is looking very, very Gaussian, with some constant out the front. And so that is the key insight. We've basically turned the integral we have to do into a multivariate Gaussian type integral, and we know how to do multivariate Gaussian integrals. So we just take this integral here and we use the fact that we know the multivariate Gaussian integrates to 1, and so that gives us an expression for integrals of the exponential of this here, and so that gives us our final result here, which is that our observed data likelihood that we're interested in is just this joint likelihood evaluated at the mode corrected by this term here involving the determinant of the Hessian. Okay, so that gives us our sort of approximate solution to this problem. And of course, it's just approximate. We don't know how good it is, but in fact, for many problems, it works surprisingly well. And so this does turn out to have wide applicability in a range of statistical settings. So yeah, so we need to calculate this mode somehow. We may as well use Newton's method because we're going to need this Hessian anyway, and so if we use a Newton type method we're going to get the Hessian along with the mode, and so given that we need those anyway, that seems like a good idea. And so if we just use Newton's method we can get the B and the H and we can evaluate this thing. We'll see an example of this in a little while. The other approach that kind of ends up winning in the end, in fact, is just to use some kind of Monte Carlo method. And so the idea behind the Monte Carlo method is that you relate integrals to expectations, and then you approximate expectations with averages of draws of random samples. Right? So in the simplest kind of pure Monte Carlo case, you might think of your problem like this, where you think of your integral as being the expectation with respect to some uniform distribution over the region you're interested in. So this is the very simple Monte Carlo method. And then that expectation, which is exact, right? So this relationship here is exact. This integral is exactly this expectation. It's kind of the definition of expectation. You can now estimate this expectation using random draws. So if we have some random draws from this distribution that we're assuming is uniform here, then we can just form their sample average of the of f, okay, applied to those draws, and that gives us our estimate of the integral. and now this really should be an approximately equal to. And oh no, that is exactly the estimator, but it estimates the true integral. Okay, because it's got a little hat on there. Okay, so that's fine. So that's our Monte Carlo estimate of the integral. And one advantage of this that turns out to be particularly important is that it's an unbiased estimate. Okay, so it's a one-liner to show that the expectation of that thing is exactly right. And that unbiasedness can have important implications in lots of examples. So, and in particular, it gives us a practical way of really getting a handle on how good our estimate is. So one problem with the Laplace approximation is it often works quite well, but it's hard to know how well it's worked. Whereas if you've got a Monte Carlo estimator that is unbiased, there are all kinds of things you can do with the theory of Monte Carlo to really get a handle on how good that estimator is, and that can be very important. We can work out the variance of this estimator. So the variance scales as 1 over n, right? We've got an n there and an n squared there. So the variance scales as 1 over n. And so the standard deviation scales as n to the minus a half, right? And that's essentially telling us how good our estimator is. And so this is order n to the minus half, which looks bad compared to what we saw for some of those quadrature rules previously, which were n to the minus 2, right? So that's much better. Okay, so this seems like it's a pretty weak method. And in one dimension, it is a pretty weak method. So n to the minus a half really isn't great scaling. N to the minus 2 is clearly much better. But the killer feature of Monte Carlo integration is that this is actually independent of dimension. Right? So let's think about that. So here, we know that in 1D we've got this order h squared, which is order n to the minus 2, but the problem that we've seen is that we need to maintain that spacing in each dimension as the dimension goes up, and so we end up with error that's not n to the minus 2, it's actually n to the minus 2 over d. And that's really the error in our quadrature rules. Okay? And so clearly, by the time we get up to d equals 4, we're at the same as Monte Carlo, and as soon as we get above d equals 4, then Monte Carlo is actually beating quadrature, right? So that's basically the story, that as soon as you're into more than 2 or 3 dimensions, Monte Carlo is going to win out, even though it's only n to the minus a half, and n to the minus a half doesn't seem that great. It's still better than what you would get from quadrature. So Monte Carlo isn't super efficient, but there are things that you can do in practice to improve it. And it's all a bit problem specific, and so it's hard to give super general advice. But one thing you could do is stratify your Monte Carlo sampling. Yeah. So if you actually just divide your integration region into subregions, then you could do your Monte Carlo estimation within each of those subregions and then combine those, right? That can actually bring the variance down. The details are not so important for this course, but that's a perfectly reasonable strategy in some cases. And in fact, this is related to the idea of quasi-Monte Carlo. So quasi-Monte Carlo is actually a deterministic set of points that are generated, in some ways a little bit reminiscent of those Gauss quadrature nodes. But the idea is it's a deterministic sequence of points that you use exactly as you would a Monte Carlo sample, and weight together your function evaluations using those quasi-Monte Carlo integration points that can have better performance than quadrature, especially in these sort of higher dimensional problems. So quasi-Monte Carlo, again, is an interesting idea, can work well in certain situations. It really requires nice domains that you're integrating over to work well, but it can work well in certain situations, so it's worth knowing about, but it's beyond the scope of this course. But if we are thinking about doing Monte Carlo simulation, then we need to think about how to do it a little bit more intelligently than we've just described, where you just do your Monte Carlo simulation using a simple kind of uniform random sample over the integration domain. There are all kinds of reasons why that's not necessarily a great strategy. So the first thing to observe is if your integral is the product of two things where one of them is a density that you can sample from, then there is a very obvious way that you can construct a Monte Carlo estimate of that integral, and that is to regard that integral as being the expectation with respect to f of phi of x. Again, that's more or less the definition of that expectation. And if you do that, then there is clearly an obvious Monte Carlo estimation strategy, which is that you generate values x from the distribution f of x, and you just average them. Sorry, you average the values of phi of x. Now, that's very simple. It's very natural. It works very well in lots of cases. So this is a sort of more intelligent version of Monte Carlo, where you're actually using the fact that you have a proper distribution in here. However, it doesn't always work well. Okay, so in many cases it does work well, and we'll see an example later actually where it does work pretty well. But the problem is that if your f of x and phi of x are very different functions, so they have appreciable mass in different places, then this approach is not going to work very well, because you're going to generate lots of values where f has appreciable mass, and if they are not the places where phi has appreciable mass, then they're not going to be really contributing very much to the integral, and really you want to be generating points where phi does have appreciable mass. So it can work well as long as f and phi are reasonably consistent with one another, but if not, then it won't. Okay, and so that can be a problem for this very simple approach. However, this very simple approach can be modified very easily by just introducing another distribution that we can also sample from just to correct this thing. Okay, so what do I mean by that? Well, suppose that G has the same support as F, and that we can sample from it. So the other thing is that if you can't sample from F, you can't use that approach that I just described. But let's assume that G we can sample from and has the same support as F. And the idea is going to be that we could choose G potentially to have points concentrated where the integrand is concentrated. So all we do is we take our original integral and we introduce a g on the top and the bottom, which obviously doesn't change anything, but what that means is that we can now regard this as an integral with respect to g. Okay? And so we can approximate that by this obvious Monte Carlo estimator, where we're averaging now with respect to the draws x from the distribution g. And then that is clearly, again, another unbiased Monte Carlo estimate. So how would we choose G? Well, what we said was we really want to concentrate points where the integrand has mass, and so that would then be the product of phi and f. So if we think about that, what if we could choose a G that was proportional to phi f? Then if you think about it, you actually get a zero variance importance sampling estimator. Now, of course, typically you won't be able to do that, but what you can do is basically choose G to make phi f over G as flat as possible, as constant as possible, and that will lower our variance of our importance sampling estimator. So that's the intuition. You try and think about this product phi f, think about where it has mass, and choose your importance sampling G function G to mimic that, and that will then give you an importance sampling estimator with low variance. So how would we do that? How would we choose a G with those properties? Well, we've seen a way of approximating functions analytically with things that we can draw from. It's the Laplace approximation. So what we can do now is combine this method of Laplace approximation with importance sampling in order to get a Monte Carlo sample in a very efficient way. So this sort of is the best of both worlds between Laplace approximation and Monte Carlo. So we're going to use the Laplace approximation to make our Monte Carlo draws in a very efficient way, but in the end we're going to get a Monte Carlo estimator that is unbiased, and so we're going to be able to get a realistic handle on the variability of our estimator. So we're going to know how good our Laplace approximation estimator really is. Okay, so that's the intuition behind Laplace importance sampling. So what are we going to do? Well, basically we're going to do some kind of multivariate normal approximation based on a Taylor series expansion one way or another. So what we're going to do is we're going to think about this product phi f, and we're going to get some multivariate normal approximation to that, and then we're going to use that as our proposal in our importance sampling estimator. So we can do all that. It turns out that rather than directly thinking about draws with respect to this multivariate normal distribution, we know that we can construct these from standard normal variates, and it turns out to be a little bit neater and cleaner to set up this Laplace importance sampling estimator in terms of draws from a standard normal, and so we just apply the transformation that we know about. So we're going to switch to thinking about Z, which is standard normal, but we're going to use this transformation here in order to get X values from this multivariate normal that we're interested in. And again, we're going to use our Cholesky factor to do that. So we've seen how to do that already. So this is all stuff we've seen before. So when we do that, we now take our integral that we're interested in, the integral of the product of phi and f. We switch variables to z. Okay, so we now turn this into an integral with respect to z, remembering our Jacobian term here, which is the determinant of the transformation. And at this point, we can now introduce our importance sampling distribution, which is going to be z. All right, so we're going to let h be the density of z, this standard normal, standard multivariate normal density. So we're going to bring that into the problem, obviously put it on the top and bottom so as not to change anything. So now we've got this integral with respect to the standard normals z. Okay, so that's what we've got. It's now an expectation with respect to z, the standard normal density, which is also denoted h. So if we now substitute in for h, we get this expression here. So this one is exact. Okay, so our integral here is exactly this expectation here, modulo that factor at the front. And the obvious way to approximate that is by an importance sampling estimator that takes draws from a standard normal. And of course, it's very easy to take draws from a standard normal. And so we get our obvious Laplace importance sampling estimator, which basically says take a bunch of draws from a standard normal, evaluate this thing and average them, and just correct them with this term at the front. And so this is our Laplace importance sampling estimator, and this can work extremely well. Like I said, in some sense it's the best of both worlds, where it uses the sort of intelligent analytic proposal of the Laplace importance distribution, but combines it with Monte Carlo importance sampling in order to get a low variance estimate, a low variance unbiased estimate of the integral that you care about. Okay, so this can work very well in practice, and we'll see that in a second. So there are a few tweaks you can do to get it to work in slightly more challenging problems. So one problem is that if the thing you're integrating has long tails, longer tails than a Gaussian. So Gaussian has relatively short tails. Sometimes if you're integrating something with longer tails, then using this Laplace approximation as a proposal can end up giving you a higher variance estimator than you would like. And so just blowing up slightly the Laplace importance distribution, inflating your Hessian slightly to give it slightly longer tails can help. Yeah, the other thing is, as I said, there's sort of typically a theta, a parameter vector theta implicit in these problems, and the idea is that you will do all of this for a particular value of theta, and then you'll vary theta and do it all again, possibly to try and maximize theta, right? So this might be the inner loop of an optimization algorithm. You might be trying to maximize theta. If you're using Monte Carlo estimates, those Monte Carlo estimates are going to be very noisy, and so every time you do this process, you're going to get a different noisy estimate, and that can really mess up optimization routines that would like to have some kind of gradient information, because if you've got a very noisy surface, then it's impossible to know what the gradient is. And so there's a trick that has many applications actually, where you draw a random set of values for your Monte Carlo estimator. So you have a random set of Z values, but then you keep those same Z values as you change theta. And if you keep those same Z values as you change theta, you actually, for those fixed Z values, can wind up with a smooth function in terms of theta. Now, at some point, there'll be bias then associated with a particular choice of Zs that you've focused on, so you might want to occasionally redraw your Zs or something like that. But it's a good trick to know about, that if you just draw your Zs once and fix them, and then keep those same Zs as you vary theta, that can give you a smoother surface that's easier to optimize. So that's a trick. The other thing worth saying is that you end up essentially wanting to evaluate raw likelihoods when in that integral that you've got, and we know that we nearly always want to avoid evaluating raw likelihoods. So we've probably got the log likelihood that we're then going to exponentiate and sum. But there's a problem there, that this exponentiating and summing could possibly lead to overflow or underflow with floating point. And so there is a trick, which is to identify your maximum log weight and subtract that out and add it back in at the end. If you're not familiar with this trick, don't worry, I'll unpack it shortly. This is the so-called log sum x trick, and again, although it has applications here, it has applications all over the place in statistical computing, so we'll look at this trick in detail later, so don't worry if it's not completely clear just yet. And again, you can stratify, and there's a standard way you could do that by mapping your Zs onto 0, 1 and partitioning 0, 1. But again, we're not going to pursue that here. What I do want us to come back to is this general trick from point number 3 here, this log sum x trick. This is a very interesting trick that has lots of applications, and so let's look at that in detail now. So very often in statistical computing, we find ourselves in a situation where we need to sum up some raw probabilities or likelihoods, but we know that in general it's much better to never work with raw probabilities or likelihoods. We always, wherever possible, try and work with log probabilities and likelihoods, because they work much better in conjunction with floating point. Yeah, so adding up likelihoods is just adding up log likelihoods is a much safer operation than multiplying together raw likelihoods. However, if we find ourselves needing to sum some raw probabilities or raw likelihoods, then how do we do that? Well, in principle, we exponentiate those log probabilities, we add them up, and then we probably want the log of the result again. So we can take the log of the result, that's not a problem. But that exponentiation operation is potentially very dangerous, because if we've got big numbers, there's a risk that when we exponentiate them, they will overflow floating point, and all you need is for one of those probabilities to overflow and you can't evaluate your sum. Similarly, if your numbers are small, then exponentiating them can underflow to 0. Yeah, so if you exponentiate a negative number, or a small enough negative number, it will underflow to 0. And in fact, if one or two of your probabilities underflow to 0, that's often not such a big deal. But if they all underflow to 0, then your sum is 0, you can't log it, and you know it's wrong, and that then is a problem. Yeah, so having any numbers overflow to infinity is a problem. Having all of your numbers underflow to 0 is a problem. So both underflow and overflow are potential dangers whenever you do this log sum x operation. And so it would be good if there was a way for us to do this operation safely, because, as I say, it is an operation that does crop up regularly in various different places in statistical computing. So the setup is we've got a bunch of log weights that we'll call L to emphasize that are the log of some raw weights W. Yeah. So we store and work with the L's. The L's are fine. There's no problem with those. We know they represent the log of some raw weight, but we also know that the raw weights could get very big or more likely very small. But the operation we want to do is precisely the log of the sum of the raw weights. Yeah, so that's the log of the sum of the exponential of the log weights. So we call that capital L. That is the operation we want to do. The question is, can we do it safely? Yeah, so the problem is that we start off with log weights, we end up with a log weight, but it's that exponentiation and summing in the middle that is the potential issue. So how do we do it? Well, in fact, it turns out that it doesn't matter whether you're worried about underflow or overflow. The same strategy fixes the problem. So what we do is we look at our raw weights, our log weights, and we compute the maximum value of those log weights. And then we rewrite this sum L that we're interested in by adjusting by this maximum value M. Yeah, so clearly that's correct. And now we can pull out that exp of M from the sum. Okay, so we do that. And now we've got the log of the product of two things, so that's just our M. All right, so our M, which is the maximum of the log weights, just stays the same at the front. And then we add the log of the sum of these adjusted log weights. Yeah, so all we've done is we've adjusted the log weights before we exponentiate them. And it turns out that that simple adjustment by the maximum, right, it obviously matters how you adjust them, but adjusting by the maximum value of the log weights is exactly what you need to do to prevent both underflow and overflow, it turns out. So why does that work? Well, first of all, how does it prevent overflow? Well, it prevents overflow because none of those log weights are bigger than 0, and so you're absolutely not going to overflow when you exponentiate 0, right? So the overflow problem has immediately gone away. What's perhaps less obvious is that you've also solved the underflow problem as well. So how have you solved the underflow problem? Well, you know that at least one of your weights is going to be exactly 0 on the log scale. So you know that when you exponentiate it, it's going to be 1. Right, so you know that there is at least one weight that isn't going to underflow to 0. Even if all of the others underflow to 0, you're going to get a sensible finite answer, and you know what it's telling you is that all of your other weights are negligible compared to that one anyway. So in any situation, you're not going to have all of your weights underflowing to 0, and the answer you end up with is going to be sensible, because if it really is the case that all of your other weights are much smaller than the one weight that has weight 1, then that's fine. That is your answer. So this solves both the underflow and the overflow problem in a really simple way. So that is the log sum x trick. Clearly, we've set it up here for just computing a simple sum, but clearly a sample mean or any other weighted sum can be handled in a very similar way. Yeah, and in each case, you adjust your log weights by the maximum and put it back in at the end. It's as simple as that, and it solves a lot of these overflow and underflow problems that involve the sum of log probabilities or likelihoods. So that is the log sum x trick. We've seen an example here where it's useful, but actually it turns out it's a generically useful thing because it often happens that you end up needing to sum a bunch of raw weights. Okay, so we've done a bunch of theory now, and so before we leave this topic, I think it's probably worth seeing how it all works out in the context of a slightly non-trivial example. So the slightly non-trivial example we've got here is the example of a generalized linear mixed model. So that means it's mixed, random and fixed effects. And the idea is going to be that we're going to evaluate the likelihood associated with this model, and the observed data likelihood, which is the thing that we're really interested in, is going to involve us integrating out the random effects B. So if you're not familiar with GLMMs, don't really worry about it. Don't worry if you're not following all of the details. It's really the big picture that we're interested in here. So we're going to start by thinking about the joint likelihood of the data Y and the random effects B. And the easiest way to do that is to start by thinking about this particular factorization of that joint likelihood as the marginal for B and the conditional likelihood of the data given the random effects. And so if we write it like that, then we can just immediately write down the log likelihood as this Poisson term for the actual so-called complete data likelihood, the conditional probability of Y given B. And then we also have this other term, which is the distribution of the random effects. So this is just the log of your independent Gaussian distribution, which is your marginal for B. Okay, so we got the Poisson likelihood on the top, we've got the Gaussian likelihood for the B's on the bottom. So this is our joint likelihood for Y and B. Okay, and of course we're working with a log as ever. Right, so that's great. But in fact, the B's are nuisance parameters here. And if we're doing some sort of likelihood estimation, say, for example, for the betas, if we're interested in those regression coefficients, then implicitly this is conditional on all of the parameters in the model, including the regression coefficients beta. We would really be interested in the observed data likelihood. That is the marginal distribution of Y with the random effects integrated out. That would be the thing we would want to maximize. And so we need a way of getting at this observed data likelihood. And the way we get at the observed data likelihood is by somehow integrating out the random effects B. Now, there are lots of ways to do it. And in fact, this problem is simple enough that, there are loads of ways to do it, and actually lots of them work okay. But it's a nice illustration of the basic problem that this integration problem, this marginalization problem crops up a lot, and we need ways of dealing with it. So let's look at some ways of how we could deal with it. Yeah, so first of all, let's make our model a bit more precise. We haven't said very much about our random effects or our fixed effects or anything. So let's just suppose we've got a very simple fixed effects component with two betas, just one continuous covariate. We're going to have the random effects as two factor variables, Z1 and Z2, each with two levels. So that means that our covariate matrix for the random effects is going to be a vector of length 4, zeros and ones in some order. And then the variance matrix for that then will be is going to be diagonal, and the first two terms are going to be the same because they're going to relate to the same factor, and the second two terms are going to be the same because they're going to relate to the same factor. Again, if the details for this are a little bit hazy, don't worry about it at all. To make this model specification precise, we can just write down some R code that simulates data from this model, right? So this is some R code that simulates data from this model that we have described. I don't think there's very much to say about it. We're just simulating some random covariates, some random effects, and they're the nuisance variables that we're going to want to integrate out. We just stitch things together, simulate, construct our predictor, exponentiate it, Poisson observations. Okay, so that hopefully all makes sense. Now, we need that joint likelihood in code here as well. So let's write that down. And again, it's the log of the likelihood as ever. So we're going to take in y and b, theta and x, and y and lambda. So theta is going to be all of our kind of parameter vectors stitched together. So it's going to be beta and the variance parameters for the random effects distribution. So we're going to split those out into beta and the real kind of theta, which is our real sort of random effects distribution variances. And here's our eta, here's our mu, here's our lambda. So this is very similar to the way we simulate the data. And at the end, we evaluate our joint likelihood using that log likelihood that we derived previously. So that's just turning that into code. All right. So that's our function that's going to evaluate our joint likelihood. And again, there's a bit of explanation in the text of what's going on here. And it does rely on this function lambda being passed in, which is going to give these diagonal elements of the variance matrix for the random effects. Now, it's going to be convenient when we want to evaluate this likelihood for lots of different b's to be able to pass in a matrix of b's as opposed to a single vector of b's, and have the likelihood evaluated for each column of that b matrix, and to have a vector of likelihoods passed back. It's trivial to adapt this function to do that. I haven't put it in the notes, but it is hidden in the notes, and so in the extracted R code from the notes we have that slightly modified version. That slightly modified version is just called lf.yb, so you look at that and just see it's a trivial modification, but it just allows you to pass in a matrix of b's, which is going to be convenient when we want to evaluate the likelihood for a bunch of different b's. So the first thing we looked at when it came to numerical integration was just quadrature. So we'll start off by looking at quadrature. So obviously we've got 4 random effects here. So this is going to be a 4-dimensional integral, which is very much at the limits of what you'd want to think about using quadrature for, but let's give it a go. We'll start off with simple midpoint integration. And so immediately we have a problem that we skipped over when we did quadrature, which is that we just assumed that the integration range was finite, a finite interval. But of course here, the domain of our random effects is infinite, right? It's a whole real line. And so we somehow need to truncate that safely. Now, because these are just simple Gaussians, it turns out that here, probably just restricting ourselves to minus 5, 5, in each direction will probably be reasonably safe. So let's just try that. And we've been through how to do this midpoint integral before, so I'm not going to go through it line by line, but we're going to use 10 values, 10 function evaluations in each direction. We're going to then use this mesh function to construct our grid at which to evaluate the points, and we're going to sum them up at the end using this log sum x trick that I've explained now. So that should be reasonably clear. So it gives us an answer, and so we hope it's a good answer, but we don't know how good it is. So how might we get a handle on how good it is? Well, one thing is we could just double the number of points in each direction. Okay, so that will obviously then be a much more computationally intensive operation, but we can just try it, and we get an answer that isn't too different, but it is a bit different. So we got minus 116-ish, and now we're getting minus 118-ish. So that, they're similar enough that you might be a little bit optimistic that this is maybe converging to something at around about that level. We'll see that, in fact, this isn't too bad. This isn't a terrible estimate. It's not brilliant, but it's getting there. And presumably if we keep doubling, we'll get closer and closer. But of course, the computational challenge of doing that will become problematic very quickly. Okay, so this is, with, as it says, even with quite a lot of function evaluations here, it's still not a brilliant estimate, but it's okay. Now, we saw that Gauss quadrature could give amazing improvements on the midpoint method, at least if the function you're interested in was very smooth. But what we're about to see now is that also it has the potential to fail, particularly in high dimensional settings like we are here, this 4-dimensional integral. And if we're using this kind of product approach to Gauss quadrature integration, and your function isn't very nice and very smooth, then it can go quite badly wrong. So let's just see how that works here. Well, we just follow exactly the same approach, except instead of using our midpoint rule, we use our Gauss quadrature, weights and nodes, and we do our we use our mesh function again to generate the correct integration points and weights associated with those integration points, and then we feed them in and evaluate our estimated likelihood again using the log sum x trick, and we get an answer, but it's quite different from the answer we got from the midpoint rule, so that's a little bit of a worry. So again, we could say, okay, so what happens if we double from 10 to 20 points in each direction? That's then, a reasonable number of points at which to evaluate the function. But if we do it again, go through the procedure again, we evaluate the likelihood at the end, we get minus 125, which is actually better than minus 136, but it's still actually a long way from the answer, and in fact it's still significantly worse than the midpoint estimate. And so that's a bit of a warning that Gauss quadrature doesn't always work brilliantly. Sometimes if the function that you're integrating is not sufficiently polynomial-like, then Gauss quadrature can fail quite badly. And so sometimes the midpoint method, although it's not as efficient, can be a bit safer. Yeah, so you could keep on going and trying to further ramp up the number of evaluation points for your Gaussian quadrature, but it just turns out that this function isn't a particularly good fit for Gauss quadrature. There are variants of Gauss quadrature, so there are smarter things you could do, and you could get Gauss quadrature to work better for this example if you knew some further tricks. But it just illustrates the point that it doesn't always work perfectly. All right, so leaving quadrature, the other thing we said, that especially as the dimension increases, is that we might want to get some analytical approximation to the marginal likelihood that we're interested in. And so for that, we saw that we could use the Laplace approximation. So for the Laplace approximation, it's not enough to simply have a function for evaluating the joint likelihood. We also need the gradient of the likelihood function and the Hessian. So again, these functions are not explicitly in the slides and the notes, but they are hidden in the slides and the notes, and so you can find these functions in the R code that is extracted from the note. So if you're interested, have a look at those. Make sure you see where they come from and how they work. Okay, so given some functions for evaluating the gradient and the Hessian, we could give a kind of very, very simple implementation of a Newton method here. So this is not a particularly sophisticated or robust implementation of Newton's method, but it gets the job done. So we start off with an initial guess at B. We evaluate the gradient using this gradient function. We evaluate the Hessian using the Hessian function. We then solve for our Newton step and map this matrix back to a vector, and then we have again a fairly simple termination criteria at the end. Otherwise we go around the loop again. So when this termination criteria is satisfied and we break from the loop, we've got our modal estimate B hat stored in B, and we've sort of got the Hessian in H. Now this is one of those typical problems where maximization versus minimization causes little bugs here and there, because the likelihood itself is something we want to maximize, whereas we're normally thinking about optimization in terms of minimization. So in fact, the Hessian at the mode of likelihood is negative definite, whereas the H that we're normally interested in is a positive definite thing, right? But again, it's just a sign flip away, so you just got to think about it and make sure you follow the signs through properly. Okay, so once we've got the B and the H, evaluating that Laplace approximation is a very simple operation, just given by this function here. Okay, and that gives us minus 116.9, so roughly minus 117. That's not bad, but it's not perfect. But the problem isn't that it's not perfect necessarily, it's more that we don't really know how good or bad it is. And that again, as we've previously mentioned, that's one of the issues with the Laplace approximation, is that it's often a perfectly decent estimate, but we don't really know whether it is or not. So that's where Monte Carlo comes in. So we could do some simple Monte Carlo first of all. So what we said was we could just divide up our range and sample from our domain of integration uniformly. All right, so that's the simple naive Monte Carlo method. So we can do that. We can randomly sample from our domain. We can evaluate our likelihood function at the points in that randomly sampled domain, and then we can average the corresponding likelihoods to get our Monte Carlo estimate of the so-called observed data likelihood, which is the likelihood that we're most interested in. And that gives us an answer, minus 119.8 for our 100,000 iterations here. So we've done a large number of function evaluations here, because we know that Monte Carlo methods converge relatively slowly. So if we're going to do Monte Carlo, we may as well just start off with a decent number of function evaluations. So how do we know how good that estimate is? Well, one thing we could do is just try doing it again, generate an independent estimate, which we do here. So this one is minus 119.3 as opposed to minus 119.8. So that's already suggesting that actually this is a fairly low variance estimate, and that this estimate is probably pretty good. All right, so we're now getting the idea that our actual observed data log likelihood is probably around about minus 119 somewhere. Okay, so that works. You can improve it a little bit by stratification, but that's a pretty simple method that works okay, at least in this problem. So in the introduction to importance sampling, we mentioned that very often there's a slightly more intelligent version of Monte Carlo you could do, which will sometimes work better, although in fact sometimes will work worse as well. And that's very much applicable here, so I wanted to mention it. So we've got our observed data likelihood that we're interested in. That is obtained by marginalizing out B from our joint likelihood. Our joint likelihood, we've already said, can be written as the product of two terms, the term corresponding to the random effects, and then the so-called complete data likelihood, which is evaluated conditional on the random effects. And so that suggests that we could think of that as being an expectation with respect to the random effects of the complete data likelihood. And so that gives us a very simple and arguably slightly more intelligent Monte Carlo approach, which is that we just sample from the random effects distribution and evaluate the complete data likelihood and average that. Okay, so we can just put that into code. In fact, we didn't have a function coded up for that complete data likelihood, so obviously that's like a special case or a simpler version of the joint likelihood, but we'll code that up explicitly there. We're going to do it for 100,000 iterations again. We just simulate from our random effects distribution, so that's this BM here. We're going to simulate a matrix of random effects from our random effects distribution with the correct variances and standard deviations, evaluate our complete data likelihood, and average them again using the log sum exp trick. So this is arguably the simplest approach we've seen so far. We're doing exactly the right thing, and the answer we get, minus 119.3-ish, is consistent with the other Monte Carlo approach that we took. So this is sort of the natural approach. It's very much kind of the first thing that I would try with this sort of problem. It's simple, it's natural, it often works quite well. The only problem is it does rely, as we've discussed, on the random effects distribution, or in some sense the prior on the random effects being consistent with the likelihood, or from a Bayesian perspective, the prior on the random effects being consistent with the likelihood for the random effects. And if that is not the case, then this can be quite an inefficient method. So this isn't the answer to everything by any means, but it's a very natural approach. It often works well when your posterior for your random effects is reasonably consistent with a prior, or the likelihood for the random effects is consistent with your random effects distribution. Yeah, so when we evaluate it again, we get a very similar answer. So that second replicate is pretty consistent with the first. Again, this suggests low variance. You can investigate this, more thoroughly, obviously. So this is nice and often works well, but not always. So in some sense, if you're not sure, you might be a bit worried about it. It will probably show up in the variance of your estimator if there was a problem with it. So if you investigated it, you'd probably find if there was a problem. But the whole point of Laplace importance sampling is that it doesn't have this problem because you're specifically using an importance distribution that is consistent with your integrand. So that's the idea behind Laplace importance sampling. And again, we've done all of the theory, so it's just a matter of turning it into code. The obvious gotcha here is that you've got to flip the sign of your Hessian to make it positive definite before you do the Cholesky decomposition. We set up Laplace importance sampling in terms of sampling relative to standard normal quantities. So here we simulate our matrix Z of standard normal random quantities. We then backsolve with the Cholesky triangle to get our matrix of B's. We then use our joint likelihood function to get our likelihood evaluations for those B's, and then we just put together our actual Laplace importance sampling estimate of the observed data likelihood. And again, this is probably the most sort of computationally efficient method we've seen so far. So that gives us an estimate of the observed data likelihood of minus 119.3-ish. And subsequent evaluations give you very, very consistent results. Okay, so this is the lowest variance estimate that we've seen so far. So again, as mentioned when we covered the theory, it's sort of combining the best of both worlds. It's using an intelligent proposal, the Laplace approximation, but it's combined with importance sampling, so you get the benefits of a Monte Carlo approach as well. So these are unbiased estimates on the raw scale. Okay, so on the log scale they're not, but back on the raw scale these are unbiased estimates of likelihood, and so you can use these to get a good understanding of the variance of your estimator, for example. Okay, so that was a nice little example just to illustrate some of the issues that arise in doing numerical integration in practice in the context of a statistical model. So I think I've covered most of these issues, although to say, once problems get high dimensional, you start getting into Monte Carlo. When they get tricky, you start kind of getting into Markov chain Monte Carlo methods and MCMC, but that's not the topic of this particular course. Also, that particular example we've just looked at, that generalized linear mixed model, we wanted to integrate out the random effects from that distribution, and those random effects were in some sense sort of nuisance parameters that we wanted to marginalize over. That's exactly the kind of situation where the EM algorithm, the expectation maximization algorithm, can be used. So if you are encountering these sorts of problems, then actually finding out a bit about the EM algorithm can be useful as well, because that can be an alternative approach to these sorts of marginalization problems. So in terms of some further reading then, this numerical optimization text, Nostal and Wright, is nice for optimization and numerical differentiation. That would be a good place to start for that. For numerical integration, Monahan is quite good. Numerical Methods of Statistics. This book by Lang is also quite handy, and this is just generally quite a nice book that accompanies this course quite well. And so, as it says here, there is some stuff on quadrature in here that might be interesting. And if you do want to start thinking about Monte Carlo and understanding Monte Carlo, then Ripley's book on stochastic simulation is a good place to start with that. Okay, so that is it for Calculus by Computer. Thank you.